Hello everyone, my name is Aya Ali and I'll be presenting on the Northern Lights. And the physics topics that I will be covering would be the electric fields, magnetic fields, and geometric optics. So starting off, I would just like to describe the Northern Lights. So the Northern Lights, also known as the Aurora Borealis, are bright lights of the aurora, and they are actually collisions between electrically charged particles from the sun that enter the Earth's atmosphere. So the lights are seen above the magnetic poles of the northern and southern hemispheres. They are known as the Aurora Borealis in the north and the Aurora Australis in the south. The auroral displays usually appear in pale green and pink colors. There are some shades of red, yellow, green, blue, and purple that were reported in some instances. And the lights usually appear in forms of patches or scattered clouds. They can even be seen as arcs or rays that usually just light up the sky. And most of the time, they are seen in higher altitude regions. So, just a bit of background here. There are many myths that are surrounding the idea of the Northern Lights. So, I thought these were really interesting. In Greenland, people held the sort of bittersweet belief that the lights were the spirits of children who had died in childbirth, and it is seen that they are sort of dancing around, like across the sky. And in Norway, the Northern Lights were believed to be the souls of old maids, which are also dancing in the sky and sort of waving at us below, if you would like to see it that way. So Galileo, obviously the famous astronomer, is the one who gave the Northern Lights their name. So he named them the Aurora Borealis, which is in Latin, it means the dawn of the north. But it wasn't until the Norwegian scientist Christian Birkeland figured out it was not what we fully understood about the Northern Lights and how they appeared. So that wasn't until 1896 where we figured out how the Northern Lights are formed. So first I would like to go over the magnetic field and magnetism surrounding the Northern Lights. Okay, so the auroras are in fact caused by interactions between energetic particles from the sun and the Earth's magnetic field. So the Earth is filled with liquid metal, and it rotates inside the Earth, which turning our planet in sort of like a magnet, a giant magnet. So the invisible magnetic field lines that travel from the Earth's north pole to its south pole is why the compasses point north, and they're following the field lines that are produced by this giant metallic magnet. So our sun is constantly releasing a flurry of energetic particles. These particles are electrically charged and driven to Earth by solar winds. So when they encounter the Earth's magnetic field, they're forced into a spiral along the magnetic field lines. They eventually will collide with either oxygen or nitrogen atoms in the Earth's atmosphere, which will then cause them to release photons of light, which caused the aurora borealis. So thanks to that magnetic core, our planetary shield is what converts these particles into the nighttime light displays. So although there can be auroras almost uh, at any place in high altitudes, we see the most brilliant auroral displays after there is a large flare on the sun. So the most powerful flares usually blast particles that are more intense, and then the auroral displays can be seen at even mid or low altitudes during some instances. So even though we are protected by the Earth's atmosphere and magnetic fields, these interactions could be very high that the auroral displays can even make sounds. So people have reported that there were some crackling noises that were coming from the sky during an auroral display. And even though the auroras themselves are at very high altitudes and the particle interactions can happen just a few hundred meters above the ground. So people have reported hearing claps and crackles during an aurora, and this can even be verified by scientists. So those interactions could be very explosive at some instances. So next I'd like to relate it back to magnetic fields. So as we know, if something is charged and moving, it would create a magnetic field. So the particles in that are colliding with the oxygen and nitrogen that are forming the photons are charged and moving. So this is why the magnetic fields are created. So to calculate the strength of these magnetic fields, we use 2 or 3 different equations. The equation that I put up on the screen is just one of them. I just put one for the sake of the presentation and the timing. So the equation that I put up there is for long straight wires, and the I represents the current, R is the shortest distance to the wire and the constant, and mu0 is the constant we use, which is 4 pi times 10 to the negative 7th TMA, or amps. So this constant is the permeability of free space, which is mostly related to the speed of light. Since the wire is very long, the magnitude of the field depends only on distance from the wire. So disturbances that are associated with magnetism in sunspot regions, called coronal mass ejection or solar flares, allow free electrons, protons, and even alpha particles to boil off into space and form a solar wind magnetosphere. Near the polar regions, because of the geometry of the Earth's magnetic field, they spiral into the Earth's atmosphere. And this is due to the magnetic force that acts on the charged particles that are moving through the magnetic fields. So the direction of that force can be found using the right-hand rule. And the magnetic fields, since the magnetic fields are circular, this rule is valid. So the right-hand rule is common for understanding the orientation of the axis in a 3D space. Most of the left-hand, right-hand rules come from the fact that the three axes of the 3D space, they have 2 possible orientations. So in order to do the right-hand rule, I went ahead and put a picture up there on the screen just to have a visual. The way that I remember it is that to find the direction of the magnetic force on a positive moving charge, obviously, your thumb of your right hand would point in the direction of V, and your fingers are in the direction of B, and the force would then be directly perpendicular to the right hand or your palm. So while doing my research here, I ran across a study which was conducted by UCLA. They used the data from NASA's Time History of Events and Macro-Scale Interactions During Substorms, and this is also known as THEMIS. Scientists have observed that Earth's vibrating magnetic field in relation to the northern lights in Canada. So THEMIS is a 5 spacecraft mission which is dedicated to understanding the processes behind the auroras. So they realized that under the right conditions, some solar particles and energy can penetrate the magnetosphere and then disturb Earth's magnetic field, which is known as a substorm. So when the solar wind's magnetic fields turn south or sun facing, the magnetic sphere contracts inwards, and then bright auroras can occur during this stage of the substorms. The new observations allowed scientists to directly link specific intense disturbances in the magnetosphere to the magnetic response on the ground. So the scientists found the aurora moved in harmony together with the vibrating field lines. So the magnetic field lines oscillated in roughly a 6-minute cycle, and the aurora brightened and dimmed at the same pace as the vibrations would be. So the brightening and dimming of these auroras corresponded to the motion of the electrons and the magnetic field lines. Here I just inserted a video. This is an animation of the Themis mission, which observes the auroral brightening. So this is as a result of a substorm in which the solar particles and energy disturb Earth's magnetic field. The Themis orbit is shown in the golden lines, which is there in the orange in the middle. While the magnetic field lines shining from Earth are shown in blue. So when solar material impacts the magnetosphere, the day side contracts inwards, while the back side, called the magnetotail, stretches out like a rubber band. So when the stretched magnetotail finally snaps back, it starts to vibrate. So this is what causes the unstable environment, and the electrons in the near-Earth space rapidly stream down the magnetic field lines toward Earth's pole. This is where they interact with oxygen and nitrogen particles in the upper atmosphere, and then they release the photons that would then create the aurora. Okay, so next I'm just going to explain the electric fields and currents that are included in the northern lights. So any charged particle creates an electric field, whether that's protons, electrons, and ions that are positively or negatively charged. Free electrons and protons are thrown from the sun's atmosphere by the rotation of the sun and escape through holes in the magnetic field. Electric currents inside the sun generate a magnetic field that spreads throughout the solar system. The field causes the activity in the surface of the sun, which surges in a regular cycle. So a solar wind, which is composed of charged particles, carries the magnetic field away from the sun's surface and through the solar atmosphere, or the solar system, sorry. So the northern lights, the flash of the northern lights, send about 100,000 ampere electric currents through the northern upper atmosphere. The electric current is a stream of charged particles, usually electrons or ions, that move through an electrical conductor or space. So it is measured as the net rate of flow of electric charge through a surface or into a control volume. Auroras are most frequent and brighter during the intense phase of solar cycle when the coronal mass ejections increase the intensity of solar wind. The northern lights occur so high up in the atmosphere that they usually don't pose any threat to people that are watching. However, the electrically charged particles that are produced could have some potential negative effects to infrastructure and technology. So the magnetic fields that are associated with these currents can reach down to induce some electric currents that are able to speed up corrosion. And it has been known to speed up the corrosion of a 800-mile Alaska oil pipeline. So that was one instance. And then the outbursts of the solar particles can also interact with the ground and knock out electric power transmission grids. So here is just a visual of what was going on with the solar winds. The solar winds and the magnetosphere consist of plasma or ionized gas, which conducts electricity. So when an electrical conductor, in this case the plasma, is placed within a magnetic field, while relative motion occurs in a direction that the conductor cuts across, rather than along the lines of the magnetic field, the electric current is induced within the conductor. So the strength of the current depends on the rate of relative motion, the strength of the magnetic field, the number of conductors, and the distance between the conductor and the magnetic field. Sorry. While direction of flow is dependent upon the direction of relative motion, the IMF originates on the sun. So this is linked to the sunspots and its field lines, which are dragged out by the solar winds. And as noted before, these particles are electrically charged and driven to Earth by the solar winds. When they encounter the Earth's magnetic field, they're then forced into a sort of spiral, which is along the magnetic field lines. So in the picture, when the charged particles from the sun strike air molecules, which are in around there in the Earth's magnetic field, they cause these molecules atoms to become excited, and then the molecules give off light as they calm back down. So this phenomenon occurs when the particles collide with atoms and molecules in the upper atmosphere, which then would transform them into a kinetic energy and into visible light. So next I'd be describing geometric optics. So actually this part of the presentation did not go as I thought it would. When I first saw the lecture on geometric optics, I thought of Northern Lights right away. And when I was doing my research, I realized that geometric optics had nothing to do with the Northern Lights. So, but I wondered if, I thought that wouldn't be true. So, upon my research, I realized that I wasn't the only one that had this hypothesis. So it turns out that Galileo in 1619 AD also had the misconception that the auroras he saw were due to sunlight reflecting from the atmosphere. So he then related the idea of auroras to rainbows. Again, this was an incorrect hypothesis. However, I will be describing what his thoughts were in regards to refraction and reflection of rainbows and the auroras and their relationship. So, rainbows are the result of the refraction and reflection of light. Refraction is the change in direction of a wave passing from one medium to another, and this is caused by its change in speed. So, both refraction and reflection are both phenomena that involve a change in a wave's direction. So a refracted wave may appear bent, while a reflected wave would seem to bounce back, sort of. Bounce back from a surface or some other wavefront. So rainbows appear when sunlight shines through water droplets suspended in the atmosphere. Each water droplet behaves like a small triangle or prism, which is reflecting the light and reflecting it back to our eyes. So part of the light that is falling on this water drop here on the screen, or any water drop, enters and is reflected from the back of the drop. So this light is refracted and dispersed both as it enters and as it leaves the drop. So the rainbows seen in the sky are caused by rain droplets, which are double refracting the light from the sun. So, and then the diffraction results in the dispersion of colors in the direction opposite to that of the rainbow. So this is how the colors of the rainbows diffract and disperse. So the refraction index, which is n equals CV, is where V is the speed of light in the material and C is the speed of light in the vacuum. So n is the index of refraction, and the index of refraction is the measure of the bending of a light or of a ray of light when passing from one medium into another. So the refractive index is also equal to the velocity of light of a given wavelength in empty space, and then divided by the velocity in a substance. So you might be wondering if refraction and diffraction are not related to auroras, how do the colors form? So the electrons that make it through our magnetosphere and into our atmosphere encounter oxygen and nitrogen. The electron transfer to these atoms and excite them to come back down. And the oxygen and nitrogen have to shoot off some of this energy, which they do in the form of photons. So then the photons, depending on where they are in the atmosphere, the electrons interact with the oxygen and the nitrogen, and then the different colors will be produced. So if the electric force applied to each bit of gas is greater than a certain level of voltage, it causes the electrons and protons of the gas molecules to be pulled away from each other. And this is how the high voltage transforms the gas into a glowing mixture of separate proton clusters and electrons. So just as an example, the oxygen up to about 850 miles will produce a nice, usually yellow or green color. And then when the electrons emit a nice red color, they're usually with nitrogen, and it's up to 60 miles in the atmosphere. So this is they are then able to mix together and then form pinks and purples and whites and sort of all the mixes of the colors. And that is all. Here are just a list of my sources. And at this point, I would ask for any questions. But I just want to thank you guys for a great semester and have a good summer.